Hello, my name is Shruti. I am a PhD student at Georgia Tech. I'll be presenting our work titled MANTIS, Time-Shifted Prefetching of YouTube Videos to Reduce Peak Time Cellular Data Usage. The load on wireless cellular networks is not uniformly distributed through the day and is significantly higher during peak periods. Wireless service providers are under tremendous pressure to either buy more spectrum or devise strategies to increase utilization of existing spectrum. To exemplify the traffic load imbalance, we performed a simple bandwidth test probe over a cellular network for a week. As can be seen, there is approximately 4 times more available bandwidth during off-peak periods than peak periods. This leaves precious spectrum severely underutilized during the off-peak periods. To address the peak load conditions, we consider the strategy of time-shifted prefetching. Specifically, we explore the problem of prefetching content during off-peak periods of the cellular network, even when such periods are substantially separated from the actual usage time. With video streaming services dominating global mobile traffic, and YouTube representing the largest share of the cellular bandwidth usage among all applications on the mobile device, we restrict the focus of this work to YouTube and explore the time-shifted prefetching of videos to mobile devices. Thus, the key question we answer in the work is the following. For a given wireless user, can YouTube videos be prefetched during off-peak periods each day so that the data usage for fetching videos during the subsequent peak hours is reduced? For the development and evaluation of the algorithm, we utilize 2 datasets. First, we rely on Amazon Mechanical Turk, or MTurk, to gather anonymized YouTube watch history from users. The users were required to navigate to Google's Takeout page and download their YouTube-related data, such as their watch history, playlists, and subscriptions data. This data was collected from 206 users and comprised of over 1.8 million videos spanning over a 1-year period. To further overcome any biases in the MTurk dataset, we also show performance results for an independently collected dataset. The data was obtained from 158 users and comprised of 17,000 videos collected over several weeks. A high-level overview of the statistics of the user and video data is presented here. The plot showing the level of viewing activity across hour of day indicates that there is a lull period from 2 a.m. to 8 a.m. This corresponds to the high available bandwidth period previously discussed. Another interesting tidbit is that on average, users watch 95% of their videos from 3 of their most preferred categories, and 63% of their videos from their 30 most preferred channels. We also find that the average user watches about 15 videos per day. Successful prefetching of YouTube videos requires the ability to predict what videos the user is likely to watch in the future. In order to study the feasibility of prefetching, we perform an analysis on our collected dataset and investigate the potential for different prefetching strategies. Firstly, a simple approach for prefetching would be to prefetch videos from the user's watch history, similar to typical web caching. From our dataset, we found that on average, 13% of videos are rewatched by the user. Thus, the potential for effective prefetching of videos simply based on what a user has previously watched is low. Another approach for time-shifted prefetching is to use collaborative filtering. In other words, we explore if there are patterns in the watch behavior of different users. We found that on average, only 8% of the videos watched by a particular user was exactly the same as another user. Due to the low similarity of videos watched across users, there is minimal scope of utilizing the watch behavior of other users for the prediction. The final strategy we explore utilizes YouTube's recommendation engine, which suggests videos that the user is likely to watch. Due to the recommendation engine being dependent on the user's live actions and the prioritization of fresh content, there is no simple approach to obtain the recommended videos that were presented to the user. So to emulate the recommendation engine's behavior to evaluate the potential of this strategy, we create a test YouTube account and programmatically replayed the user's watch history for 1 year. We found that a relatively large fraction, nearly 70% of their future video watches previously appeared as a recommendation. As a result, using recommended videos as the candidate set from which to prefetch videos is a promising solution. However, one of the key challenges is that even with the focus on recommended videos, the size of the candidate set is going to be large enough to prohibit prefetching the entire set. With this core insight, we propose an intelligent prefetching algorithm, MANTIS, that accurately predicts videos a user will watch from her candidate video set while ensuring an acceptable prefetching efficiency. There are 4 parts to MANTIS. First is the candidate set generation, then feature selection and engineering, the classifier design, and finally, system implementation. We have shown that the recommended videos based on the user's watch history is a promising candidate set. However, as YouTube's recommendation engine cannot be precisely emulated, we cannot obtain the exact videos shown to the user as recommendations. As a result, a major caveat with utilizing the recommended video set is that the classifier cannot operate until the training period is complete. To address this issue, we explore an alternative set of videos for the candidate set. YouTube algorithmically determines videos that are related to one another using the video's metadata, which are independent of the particular user and their watching behavior. These videos can be retrieved using YouTube's data API. We found that for 10 randomly selected users, that the percentage of videos watched from the recommended video set is on average only 4% higher than the percentage of videos watched from the related video set. And so, given these results, we utilize the related video set as the candidate set from which to prefetch. In order to populate the candidate set, we consider a set of videos M that were watched by the user over a certain number of days prior to the prefetch day. This period is termed as the generation period. And so, for each video MI watched in the set M, we add its 50 related videos to the candidate set. To select the generation period, the percentage of videos watched from candidate sets with varying generation periods is computed. The generation period yielding both a high hit ratio and acceptable candidate set size is selected as 14 days. So for the average user that watches 15 videos per day, the candidate set size can potentially include as many as 10,500 videos. To accurately select a few videos from such a large candidate set, being able to effectively encapsulate the user's viewing behavior is pertinent. Thus, the features that are used for the classification algorithm are of great significance. For example, if this video appeared in the candidate set for a particular user, the features related to the video that we consider are the number of views, likes, dislikes, and comments it has, the video duration, also the number of subscribers and uploads the channel has. For user preference related features, a Boolean feature indicating if the user has subscribed to the channel is used, a similar feature for whether this video appears in one of the playlists is considered, and in addition, the difference between the upload date and the prefetching day is computed. The tables here summarize the features selected for the prediction. In addition to the features shown in the example, the video tags, date the related video was watched, the number of times the video was previously seen, and the category ID is used. Given that there is a sizable amount of data to be considered for accurate prediction of videos, utilizing all the features is computationally expensive. MANTIS eliminates this redundancy with the application of principal component analysis. We found that approximately 95% of the variance is captured within the first 11 principal components, and so the dimensionality is reduced accordingly. Once the features have been selected, the classifier is designed. There are 2 facets to MANTIS's classification algorithm: training and prediction. For each day in the training period, the candidate set is populated by obtaining the related videos and its metaset. Then the set is pruned by selecting videos from their 3 most preferred categories and 30 most preferred channels. And finally, each video's classification attribute is set as being chosen if it was watched on that day or discarded if it wasn't. Once the training phase is complete, the prediction phase can commence. In this phase, a classifier is designed to make a prediction of what video the user will likely consume during the next peak period from a populated and pruned candidate set. A classifier that we hypothesize will be well suited for this data is the k-nearest neighbor classifier. To validate our hypothesis regarding the choice of this classifier, we implement the aforementioned training and prediction and compare it to 3 other popular machine learning algorithms. It can be seen that the KNN classifier does indeed perform better than the other methods, and so we utilize KNN as a classifier for MANTIS. The architecture consists of a MANTIS server and a MANTIS client, with the server residing on a cloud infrastructure and the native client app on the user's mobile device. MANTIS is provided as a service to which a user subscribes to during the startup mode. The user's watching related data is sent to the server for training. After the user has subscribed to the MANTIS service, the MANTIS client performs in steady state mode, in which videos are prefetched daily during off-peak periods based on their most recent watching behavior. Essentially, the user's watch history, subscriptions, and playlist data is sent to the server once during startup mode and daily during steady state mode. The server predicts the videos that will be watched and sends the client a list of those titles via the mobile sync module. The client app then interacts with the YouTube app to download the videos. YouTube's offline download feature, which enables seamless injection of the prefetched video content, is utilized as means of prefetching the videos. So, in order to evaluate the performance of MANTIS, we study the impact it has on bandwidth consumption, analyze how well the classifier performs, show results related to a prototype implementation, and also perform a user study. The parameters used for the evaluation are shown in the table. The value of K and the training period were empirically determined. The cache is completely replaced during each prefetching session. When MANTIS is implemented and videos are prefetched during off-peak hours each day, there is a decrease in the bandwidth consumed by the users during peak periods. We evaluated MANTIS for 30 continuous viewing days for each user in our dataset and found that MANTIS is able to achieve a peak time bandwidth reduction of 34%, while increasing the overall bandwidth consumption by 12% during off-peak hours. In order to evaluate the classifier performance, we define the following metrics related to prefetching accuracy, efficiency, and overall classifier accuracy. We see that MANTIS is able to accurately select 79.3% of the predictable videos from the candidate set, and of the videos that are prefetched, 79.1% of the videos are watched by the user. Furthermore, MANTIS is able to correctly classify 83.2% of the videos in the filtered candidate set. In addition, comparable results were obtained for the independently collected dataset. We developed a proof of concept prototype of MANTIS, which uses macros to schedule and sequence the various tasks on the MANTIS client during the steady state mode. The prototype was evaluated for 10 users over 5 days. From the results obtained, we can see that the MANTIS app is indeed lightweight and does not burden the resource-constrained mobile device's power and storage consumption. And for the user study, we recruited 10 volunteers and deployed the MANTIS prototype on their mobile devices for a period of 2 weeks. The average prefetch accuracy and efficiency is 71% and 69% respectively. This is comparable to results achieved across the MTurk dataset. We also found that nearly 48% of peak video traffic was shifted to off-peak periods with the use of MANTIS, which is considerably higher than the 34% obtained across the MTurk dataset. A potential reason for this difference could be that the candidate set is populated at the time of prefetching as opposed to ahead of time. So to conclude, we address the problem of high peak cellular traffic through MANTIS, which is a time-shifted prefetching strategy for YouTube content. The smoothing of the network traffic curve is approximated here if we assume a uniform distribution of prefetching times for the users in our dataset. We found that an overall reduction of 34% in traffic during peak periods was achieved through the employment of this algorithm, while increasing the overall bandwidth consumption by 12% during off-peak hours. Thank you very much.